All right, guys. So probability of C is just 0.61. Is that? Everybody see that? This kind of problem is a problem that I like. I should tell you something. Probability B. California registered voters who say the Supreme Court's ruling about the constitutionality is very somewhat important. Yeah, 6 in 10 California voters said that the upcoming Supreme Court's ruling was very or somewhat important to them. That's exactly what they're talking about there, right? So 6 in 10 is 60, right? And now, can somebody, now what's A? A is voters 18 to 39 years old. So can somebody tell me, C given A, what is this in English? Well, how do you read that in English? The probability that you pick a words. California registered voter who supports same-sex marriage, given that they're 18 to 39 years old. I like it. So what else do I know? Let's go through the, I know A and B asked me this already, but is there anything else they told me that I haven't assigned symbols to? So for example, that second sentence, among 18 to 39 year olds, the approval rating was 78%. So how would you... So among 18 to 39 year olds, what does that relate to in probability? Among 18 to 39 year olds. So could it be a 40 year old? So what does that relate to? What word? Sure, but probability wise, what word does that relate to? How do I constrict what I'm looking at? Throw some people out. If I am given. What have you been given? Among 18 to 39 year olds, what do you know about the person? They are 18 to 39. Given that they're 18 to 39, and what letter is that? A. So given that they're 18 to 39, among 18 to 39 year olds. So given that they're 18 to 39, the approval rating was 78%. And which letter is that? A is the 18 to 39. C is the voters who support same-sex marriage. So hey, holy shit. And that's what? That's the second line. So that's, what was the percentage? 78%. So look, isn't that question C? So really, when I'm given this problem, I'm going to take each percentage they give me and assign symbols to it that go along with the idea. Do you follow? So they kind of gave me these symbols, and that won't always be true, but I just make my own symbols. So if I said, out of 10-year-olds, 30% had brown hair. All right. So that's probability of brown hair given 10-year-old, whatever symbol I want to use. T for 10. Yay, Jeff. You got to give yourself symbols to work with. This is very much like algebra, where you give yourself X and Y and all that kind of business. But now it could be any damn thing related to what the actual situation is. Let's see, anything else we left out? Let's see, the very last line. Out of those registered voters who support same-sex marriage. So again, what does that relate to? Out of those California registered voters who support same-sex marriage, that's related to C. I like it, but what idea? Given. So given C, 75% say the ruling is important to them. B. And that's part D. Holy shit. So this is that problem where everything was spelled out to you. You just had to... This whole problem is, can you convert all this frickin' English, too many words up there, shit, into nice shorthand. Nice shorthand. Those weird-ass math people, we love it. But I'd rather say PC is 0.61 than a field service is 67%. Oh my god, so too many words. Yes?
Why is probability of being 60? I just missed it.
Oh, so the last thing, out of California registered voters, out of those people, so given that it's one of these people,
right?
And so which letter is that? The C. So given C, 75% say the ruling is important to them.
Right.
B, the percentage who say it's important to them, given that they're California registered voters who support it, is 75%.
No, like the actual problem B, probability of B is 60. What you wrote right there.
What's happening?
The middle of number 2.
Oh, here?
Yeah.
So that was 6 in 10 California registered voters said.
Got it. I just missed it.
I got you.
Thank you.
Yes?
Two questions. First one, that C given A should produce the C or should produce A on that up there.
I like it. R, C, and A. I think this goes on to the next page, right? So we're almost
Yes,
there.
and the other
Well,
thing-
just watch. Are C and A independent events? What's the probability of C by itself? 61%. What's the probability of C given A? So if A happens, does C change? So does the probability of C depend on if A happens or not? Let me try this again.
No.
C by itself is 0.61. If A happens, does C change?
No.
Yes.
How else can I say this? What does that mean in English? The probability of C happens given that A happened. So if A happens, given that A happened, does the probability of C become something different than 0.61? Yes. So they are dependent. Don't make it more than that. It's nothing more than that. That's all it is. So if, given that something happened, does the probability of this guy change from what it was before, then they are dependent. Because if I say, what's probability of C? Well, it depends. Did A happen or not? Because if it did, then it's 0.78. No, yes. That's what dependent means, and it makes actual physical sense. C cares if A happens because it actually, the number for C changes. The probability of C is 0.61. Here, the probability of C, given that A happened, becomes 0.78. It increases. And so if I know that the person is younger, then the percentage who support it is higher. That's what that means. Which, makes sense if you think about the issue.
So that means that that group, 18 to 39, is part of the 61% registered voters.
Yeah, this is independent of, it could be anybody.
Yes. But they are.
But if I look only at the people, the younger people, then the probability that they support it goes up.
Goes up.
If I look at a different group of people, it's going to probably go down to average back out to be 0.61
Yes.
total.
And my last question is about that 75%. It says just it's important, but the B assigns to very or somewhat important.
Yeah, so when they say important, they mean any kind of importance. Any kind of, they should have been more specific there, but there's no way to figure it out otherwise, so they must have meant any kind of importance. Very or somewhat.
Yeah, therefore it's part of the. Okay.
Otherwise, there's no way to solve that.
Okay.
Is there more problems to that? Let's see. Yes. Oh. All right, I don't have to do that anymore, Jeff. You can do this. There you go. All right, in words. Well, we got to remember what the heck that was. What is B given C? Well, B was, it's very important to them, or somewhat important to them. And C was support same-sex marriage. So B given C would be, what's probably that, or they're somewhat important to them, or very important to them, given that they support same-sex marriage. So that's all it is. If I see B, holy crap, line C, the phrase that is B, then put the word given, and then the phrase that is C. I'm just directly translating from math to English. So it's sort of like, instead of inputting 7 for X, I'm inputting a sentence for B. And I'm inputting a sentence for C, and of course I'm inputting the word given for that line. What we do is that decent. So translating here is pretty easy, because they told me what A, B, and C were. Just let's stick them in. What about this? Now we get more interesting. Now we finally get something I have to calculate. Find the probability of C and B. So what is the formula? Let me just jump down to G. That's more interesting. the probability of C and B. What's the formula for that? Somebody help me out.
Multiplication.
Multiplication. I like it. Totally. Be a little more specific. Nope. Only if they were independent. In general, what is
C
this?
given B?
The probability C, that's already up there,
Okay.
times
B
the
given
probability
C.
of B given C. This is sort of like a king times, and then you decrease the number of cards because you already picked the king out, that kind of thing. The second guy changes depending on what happened in the first place. If they're independent, this is B. So then it would just be the straight up. If they're mutually exclusive, then I don't have to subtract anything because that would be 0. See, so and is basically multiply, but you might have to adjust the second dude, or is basically add, but you might have to adjust, subtract some stuff off because you counted somebody twice. It's a beautiful kind of symmetry there. Yeah, I love it. Sorry, you have an amused look on your face. It's different for me. Okay. So now I just got to plug this in. I know what probably C is. Do I know B given C? Yeah, I totally do. Sweet. So if I would have written like this is also true. I could have written probably B times probably C given B. But do I know C given B? No, so screw that one. So then I just got to plug and chug. So it's all about knowing the formula. So this is that kind of problem I was warning you about. You have to use the formulas here because they didn't give me a table that I can count people. If I give you that, forget the formulas. You got to trust me on that. Forget the formulas. They always mess people up. Just count and go. When I don't give you something to count, I just give you numbers. Oh shit, you better get those formulas out and just start plugging and chugging. Alright. Alright. I'll let you guys finish that one out. Yeah. Anything else from homework? Yeah.
92? Or 91?
You can almost see it. Oh, this is semi-silly. Alright, so let's do this. If I tell you two events are mutually exclusive, and I know that's not what it says, and I don't care, I'm doing like a little review. Mutually exclusive, what does that mean? If I tell you that A and B are mutually exclusive. Say again?
If one happens, the other one doesn't happen.
A can't be B.
Yeah, they can't be each other, right? So it could be like, I desperately have to find something that there's no cartoon for. Like, if I pick a pet up, one pet, could it be a hamster and a llama? There's no hamster and llama yet. You can go make that show, but it don't exist yet. Don't give me that shit. Hamster llama, whatever. Get some crazy adventures. All right. So hamster and llama are mutually exclusive because the probability I get a hamster that is also a llama is 0. So if I tell you that two things are mutually exclusive, you can automatically write this down. Bam. That's a known fact. You write that down immediately, so then if you need it, you got it. Now, same way. What if I tell you that they are independent events? If I tell you that A and B are independent.
The occurrence of one of them doesn't change the probability of the other.
Sweet. Now, less words.
If B happens, it doesn't change.
No, too many words.
A and B is P.
Probability of,
A and B.
no and.
A given B.
A given B.
Equal to A. Probability.
Probability of A. Given that B happened, A doesn't give a crap, right? Whatever A was, it stayed the same. someday I'm going to learn. I just can't, I don't know. I don't say that right. The idea is so straightforward, and I think you guys want it to be harder or think it's going to be harder. If B happens, and the probability A is the same as it was before B happened, did B affect A? Therefore, I would call them independent. I mean, it only makes sense. Some of you guys are like, yeah, easy for you, math boy. But trust me, you got to come back a level. Don't try to make this more than it is. That's why we call them independent, because one thing happening doesn't change the other probabilities happening. So right here, Y and Z are independent events for number 91. So what can I immediately write from that statement they made? Y and Z are independent. No. Didn't say mutually exclusive. Thanks for playing.
Y given
Yes.
Z
Y given Z
is Py.
is Py. I like it. Or Z given Y, probably Z. One happening doesn't change the other one. Doesn't care. Oh, you happen? Really? That's nice. If you could hear the conversation between the events, that's what they would say. Really, you happen? That's good for you. All right, so then it says rewrite the basic addition rule. Now watch, you ready? So if I know that they are independent, there's a way I can rewrite this. This part right there. What's the formula for probably Y and Z? The formula for the probability Y and Z. We just used it a minute ago.
Multiplication?
Yes, it is. So like probably Y times the probability of Z given Y. But what we just say is true about Z given Y.
If it doesn't change.
Equals PZ. This is the one time you can just straight up multiply two things, is if they're independent. If one happening doesn't change the problem. The one time you can straight up add two things is if they're mutually exclusive. There's nobody to subtract because you didn't count anybody twice. It's a nice analogy there between or and. So I can rewrite this and as probably Y times probably Z. Just plug that in there. That's a very vague question, I agree with you. So it's a good question to ask. Because it's like, rewrite what? But this is the only thing that's related to this given stuff. So that's what you can rewrite. I can put this there. And now I can use part B. They tell me what everything I need is. I can just throw it in there and solve. Right? Replace, what did I put? Oh yeah. So replace Y or Z. They tell me it's 0.71. They tell me the probability of Y is 0.42. 0.42. Oh shit. It's going to be algebra. Sort of like Indiana Jones. Why did it have to be snakes? Why did it have to be algebra? So they write Y or Z. What do I put here now? Here, instead of and Z, I can put this. Okay, so what does it mean for two things to be independent? The given is the same as it was before. So any formula that has that in it doesn't need it anymore if I know that they're independent. So all I did was replace this with Py times Pz because they're independent. I can do that. And now what do they tell me for part B? They tell me that Y or Z is 0.71, and they tell me that Y probability is 0.42. And I just don't know what probability Z is. So you gotta solve for P of Z. Now, what is a whole P of Z minus 0.42 P of Z's?
0.58.
5/8, there it is. So P of Z is acting a lot like in algebra is acting like X now because it is a thing I don't know. So I can treat it just like X. I can combine like terms. Good old algebra. This is the most algebra you'll see in this class. We will see some more algebra later, but this is the most you'll see, like solving an actual equation. It's not even hard. 2 more steps after that, you're done. All right. So if I were you, I would realize that I am probably going to give you problems where I say, hey, event C and event M are mutually exclusive. And then I ask you a bunch of stuff, and some of you guys would be like, I don't know enough to answer this stuff, but I told you they're mutually exclusive, C and M, so what can you immediately write down? Probability of C and M equals 0. And then you can throw that into any formula that you need after that. So if I say mutually exclusive, I'm telling you that. If I say independent, I'm telling you this kind of thing. Yes?
So when you use the equation where it's like P, the probability of A given B equals the probability of A and B over probability.
Well, that's the formula, yeah. That's where this formula came from. Totally. I mean, that's the same formula. So the probability of y, Z given Y equals the probability of Z and Y, right? Divided by the probability of Y. If you multiply that up, you get that. Same formula. This is the basic formula for a given. I love you guys. What's the problem? You alright? You're all sitting there saying, I can't believe this. No. So then you have to ask questions. I mean, it's the way it works. So what's up? What is it about that problem we didn't like? No. It can't be true. Yeah.
So you always use that equation unless it says independent?
So this equation, guys, this equation is always true. This is the definition of C given Y. Let me just stop there for a second. This equation is always true because this is the definition of Z given Y. Now we've done problems. Let me remind you. Tell me this. What's the probability that I pick a king out of the deck of cards? 4 out of 52, which reduces to 1 out of 13. What's the probability I get a king given that it's a club? What's it out of now?
1 out of 13.
It's 1 out of 13. Are these different?
No.
They're the same. But what formula did we use to calculate this just now? That one. Where is it 1? Because there's only one card that's a king and a club. And why did I put 13 on the bottom? Because that's how many clubs there are, right? So that formula is never not true. Stay with me now. I love you guys. This formula is true. It's the definition of what given is. But if I do the formula and I get the same number that I got for the thing by itself, then what's true about these two things? They're independent. That's the check. So this formula is never not true. I love double negatives. I love it. Because in math, we don't negative is positive. This formula is always true. If you do the formula and it comes out to be the same number as it was before, they're independent. Did the king care that a club happened? No. It's the same chances. It's got the exact same chances, so it didn't care. I don't understand. What's that? We've done this before, yes.
I get that it's the same numbers, but you're basically using like a different set of numbers, I guess. Like the answer is the same, the probability is the same, but
Of course you
are
are.
they independent because it's still like changing the numbers you would be using?
No. Guys. Probability doesn't care what the fraction looks like. The decimal doesn't care that it's 4 divided by 52 or 1 divided by 13 at all. These are the same number, right? Guys, these are the same number, right? So does the chances that a king happens change if I tell you that it's a club that I'm holding? No. Therefore, the probability of a king happening didn't change, so the king doesn't care that a club happened. It still has the same chances of winning, same chances of being in my hand. Your point is a good one. It's a different numbers, it's a different amount of cards, but percentages don't care how many. If I told you 11% of the people outside like tomatoes, do you know how many people that is? No, because I don't know how many people are outside right now. But 11% doesn't care how many people are out there. It'll change the how many, but it's still 11%. And I said, oh, if I go to Mesa, it's still 11%. Well, then it's independent of which college I'm at. And how many people at Mesa? Who cares? It's still the same chances. It's still 11% chance. Does that make sense? Percentages don't care how many it's out of. 11% of 80 is 11%. They're not the same amount, but it's still the same percentage. It's still 11%. So it doesn't matter if you talk to 80 people or 800 people. If it still comes out to be 11%, the percentage didn't change. That's what's important here.
So if they're independent events like that, will they always be like this? Will P of K always be the same answer as P of K given something?
That's the definition of no. Not something else. If king and club are independent,
Like, will they always be the same percentage or fraction?
yeah.
They're independent.
If A and B are independent, then whatever probability of A is the same as this. Period.
Okay.
That's
so they're always going to be the same. That's
yes.
another-
In fact, that is the check. If I say, are these independent? This is what you must check. And if you'll notice, on that practice thing we did the other day, this was part A, and this was part whatever. I make you do the work. You just have to go find the things to compare. That's all. Okay. Anything else from homework? So guys, I need your help on something. You're a college student, and you're not sure what something means or how to do something. What do you do about that, besides complain in class? Yeah, it's crazy. You get help. Holy shit. So you go to the Math Study Center, it's free. You go upstairs and the tech ball is free. Go see me in my office hours. That's free. Right? You know how expensive I'd be if I put myself on Craigslist? Really, because I don't know who's coming to see me. They could kill me and I could be the next movie of the week on Lifetime. The Craigslist, all I wanted to do was help them. Yes?
You said the math totals in a total.
Yeah, it's really bad.